Hello and welcome to another video from the only channel that you need to not only survive the current apocalypse but actually enjoy it. And today's video is going to be the next installment in my Debunking Flat Earth video series. Now in this particular video we're going to take it from a completely different angle. We're not actually going to be debunking flat Earth, we're simply going to be proving sphere Earth, because it's very obvious to anybody out there that the best way to end the argument is to simply prove that the Earth is a sphere. That way we don't have to discuss what the shape of the Earth is. Now, obviously, the most simple way to prove what the shape of the Earth is to take a rocket, go into outer space, and when you get far enough away to see the whole thing, just take note of what shape it is. And in fact, there are men who say that they have done exactly that. And in fact, those men came back with photographs. However, in this particular instance, I must side with the flat earthers who say that those photographs are very questionable. And if you listen to anybody who's done any research into the photographs that were brought back by the astronauts who have been into outer space, it becomes very obvious very quickly that something just doesn't quite add up. But even if those photographs are 100% legitimate, we know that it is not that big of a deal to create photographs out of thin air. Hollywood does it all the time. So photographs from people that we do not trust are not proof that the Earth is a sphere. But it doesn't really matter, because whether those photographs are real or not, whether the men who say they took the photographs are trustworthy or not, we don't need them. We can see for ourselves what the shape of the Earth is without ever leaving this planet. Now, just so you know, one very easy way that I would think to prove that the Earth is a sphere would be to simply travel around it. Go down to the equator and just travel all the way around the Earth until you end up back at the same spot where you started. Seems to me that would be simple enough right there. The problem is that flat earthers have an answer for that, and you can't simply dismiss something someone says just because they're unreliable. You have to figure that if they're saying it, there must be something to it. What they're telling us is that on a flat Earth, here's the North Pole, here's the wall around the Earth, and I do not understand how this works, but apparently if you're out here traveling, and this is the equator, somehow the space-time continuum does not work in our understanding of directions. I do not understand it. Supposedly the sun and the moon are traveling like this over the flat Earth, and if you start walking a straight line, no matter how hard you try not to walk in a crooked line, you're going to walk in a circle. I have absolutely no idea why they say that, but there's a whole lot of people that are willing to die for that belief, so we have to imagine that there's at least something to it. All right? I'm not making fun of anybody here. I'm just saying that if that's the teaching and enough people believe in it, then it's not for us to just dismiss it. We have to somehow prove them wrong. Not to them. Remember, flat Earth is a religion, and just like any other religion, reason goes out the door. So there's no sense in taking this information I'm sharing with you and sharing it with a flat earther, because all it's going to do is make them mad. They are not going to change. So, okay, we know that going around the equator isn't going to work. But how about if we decided to do it a different way? We're going to travel around the Earth until we come back around the other side and once again meet up. Because you can't. If you say that you went across the North Pole and across the South Pole, then that pretty much crushes the only working theory that I am aware of about where the edge of the Earth is, because I have never seen somebody say that the edge of the Earth is somewhere else. But even then, if we want to be reasonable about that, we probably ought to go a few different directions. So say we go out this way, and then maybe cross over here, just keep going round and round and round and round. Well, eventually, we're going to be going somewhere real close to somewhere we went before, and we're going to start seeing the same landmarks. So we'll know for a fact that we have covered every inch of the Earth. The Earth is a sphere. There's no denying it. And, you know, and we win. We win. The Earth is a sphere. But I'm going to show you a way to do that same thing without having to put so much effort into it. That's a lot of work. Probably be a lot of money too, because you're going to have to eat, probably wear out some shoes. So we're going to look at every inch of the Earth, and we're going to do it from our backyard. We're not going to be able to see every inch, but we'll see most of it. Okay, let's just imagine, first things first. Most flat Earth, or most sphere Earth, is based on the very basic fact that if you take a telescope and you go out to sea and you look over the waves, you're going to see ships sailing away. The farther they get away, the lower they look in the water. So initially, you'll see something like that. But as it gets farther and farther away, you'll eventually see something like that. Of course, it's getting smaller all the time too, but I can't do it smaller and you still see it from that camera. So eventually you're just going to see the mast and eventually nothing. And we're going to explain why that is. Because the Earth, that effect is caused by the curvature of the Earth, according to sphere earthers. According to flat earthers, that effect is caused by, I don't know, magnetism or heat or radiation or something. Okay, that looks really, really flat because it basically is. But if we are out over here in our house and somebody's over here in a ship, we have no problem seeing the whole ship. That's where it is. But eventually, as the ship travels farther and farther away, it will start to be obscured. The view of it will be obscured by the curvature of the Earth, so much so that we won't even see it. So say we're on an island here, and we're in a boat here. What's going to happen is this hump is going to be too tall for us to look over to see the boat. And in the ancient past, people who had to go out to sea, say fishermen, would never go too far away so that they could get lost. Because once you get over this hump, then suddenly your ability to see the land is gone. So let's just explain why that is. You're in a boat right about here. There's this big hump caused by the curvature of the Earth. And once that hump gets taller than your land or your boat, you're not going to see the land, and people on land are not going to see your boat. So, what eventually happened, you know, because no one is going to go out there past that mark. Once you get past that mark, the ocean looks exactly the same in every direction. It does not matter where you are in the middle of the sea, you're in the middle of the sea, and that's all you can tell from looking at the ocean. You have lost what are called landmarks. Your landmark is here, it's over the hump of the Earth, now you're lost. And so at some point, men started to put sails on their boats, and people in the boat could climb up on top of the mast, and if their mast was tall enough, They could still see land, see the very edge of it. And they didn't put these masts on there so that a man could climb up there. They put the mast to hold the sails. But they figured once the mast is there, they might as well put something up there to make it easy to sit there and watch. And they call this thing up here a crow's nest. And a crow's nest isn't necessarily like in the movies where you got like a basket up there. Sometimes a crow's nest is just a rung of a ladder, you know, or a little pedestal maybe that big that you could stand on. But that didn't solve, you know, that was not the end of it, because eventually men weren't just going to sea to fish. They were going out to sea as a part of their commerce, their economic systems. And so they wanted to go farther out to sea. And so the people on land started putting up towers. And they would put lights on the top of the towers. And the light wasn't necessarily just because of nighttime. It was because basically a human can only see about 12 miles. And that's irregardless of, you know, which direction you're looking or how tall of a tower you got. If you've got a tall enough mast and a tall enough tower and it's 20 miles away, you still won't see it because of particles in the air. And by particles, I mean oxygen, nitrogen, carbon, all of that stuff is in the air. And over a long distance, well, you just simply can't see. But even though you might not see the tower and you might not see the light, or you might not see this structure of the light, you will see the light itself past 12 miles because that light can cut through those particles. So you can actually extend out, and I'm not really sure. I think I was on a lighthouse tour one time and they said you could see, I don't know, around 20 miles out to sea. And so that extends you to about the maximum amount that you can go by using what are called landmarks. But sailors didn't simply stop at 20 miles, they went farther. So we're going to examine how they did that and how that applies to us today. Because even though for the most part, you navigate by terrestrial landmarks, once your terrestrial landmarks go away and you're out there in the quiet of the sea, and nighttime comes and you're laying on the deck of your ship, you're going to start to notice the celestial landmarks. Because even though you may not be able to see this, you can see that. Stars in the sky. Now, I just said that you can't see more than 20 miles for a light. And as far as just structures, you can't see more than 12 miles. And that's only on a very clear day. If it's foggy, or if there's a lot of pollution, if it's raining, snowing, you won't see that. So how are we going to see stars which are millions of miles away? Because these particles are all down here. This is our atmosphere that we breathe. Now you get up a little higher, you still got atmosphere. In fact, you can go climb mountains. And some people who are very adapted to that can climb very, very tall mountains without any kind of oxygen bottles or anything. But the air is extremely thin. The farther up you go, the thinner it is. And so if you're looking up at a star, you're not going to be looking through 20 miles of this. You're going to be looking up through a whole lot less. You're only going to be looking through a few miles of the dense particles, and then you've got many miles of very, very light particles, and then there's nothing. Because space out here is supposed to be a vacuum, according to the religion of science, and that actually sounds reasonable to me. You may be interested in how you can use a star to navigate. Well, I'm going to show you. If we're on the Earth, pretty much kind of looks like that. But when we look at a globe, it doesn't look like that. A globe looks like this. And I guess most people take these lines for granted. They don't really understand what they mean. It's just a grid system for marking off who owns what territory or something like that. But these These lines have actually been on our globe for thousands of years. This is part of an ancient religion called sacred geometry. And sacred geometry was practiced back in ancient Egypt. Each of these lines is represented by a star. And the reason for that is that our universe, the stars in our universe, never move. I mean, they move probably, I don't know, a million miles an hour or something, but they're so far away that that movement is imperceptible to us, especially over the course of the average human lifespan. You know, if you go out in your yard when you're a child and you look up at the stars, you're going to see basically the same pattern that you'll see on the day that you die. Because humans just don't live that long. The stars are very far away, and for the most part, their movements are pretty much set. So if you're here on the Earth, and you look straight up, and you see that star, if you go out there 50 years later and look straight up, you'll see the same star. Now, there is an issue with that. Our Earth is spinning. So you only get to see that star once a day. It's only going to be there once a day. And it's not once every 24 hours. It's a little bit different because you have a difference between the solar year and the sidereal year. But the fact is that star never moves. But that explains, but the Earth does move. And that explains these marks. Why they're here. These marks are not directly under any stars. These marks mark off something else. They mark off time. I don't know how many people know this, but these lines, there's 360 of them. These lines, there's 360 of them. And in fact, anytime you are working with circles, you're working with 360 degrees, because that's how many degrees or marks are in a circle. Now, if you notice, these go all the way around because they always stay under that star, but these all meet up at the North Pole and the South Pole. And the reason for that is that these marks are marking off time. You see, back in the ancient past, the Earth had a 360-day year, so it just seemed reasonable to put 360 lines going each way. And when humans decided to divide up the day into hours, minutes, and seconds, this system still worked, because you got 60 seconds, which is divisible by 360. You've got 60 minutes, which is divisible by 360. You got 24 hours, which is divisible by 360. So what you end up with is a very dependable system for determining where you are. So if you know that your house is here and you're over here, you could look up at this star and know that if you can get up underneath that star, you are going to be home. Now, only problem being that since the Earth is turning, you have to be under this star at the right time. But you can always know what time it is back in the ancient past by simply looking at the moon. Remember, at one time, the sun and Earth and moon were in conjunction. The Bible confirms it, the Mayan calendar confirms it, everybody confirms Earth-wide that at one time, every human on the planet thought that they had a 360-day divided by equal 30-day months, 12 equal 30-day months. And so, if everybody believed it back then, it must have been true. And if they were willing to divide the Earth up into 360 sections going either way, that's a pretty good indication that these guys were not stupid, people that did that. So anyway, in a perfect world where the sun is always in the daytime sky and the moon is always in the nighttime sky, you can always gauge where you are in the stream of time simply by looking at the position of the moon. If the moon is straight overhead, then it's midnight. But of course, you don't need to know what time it is where you are. You need to know what time it is where your star is. And so a system was established even back then for gauging where the moon was relative to the stars behind it, where the sun was, where the stars were, and just from that being able to tell exactly what time it was wherever you were, what time it was at your destination, as well as where your star was. Because if you're here, you want to get here, all you got to do is keep aiming for that star. And not just that star. because there are thousands of stars in the sky, so as the Earth is turning, it might be a different star over each one of these grid points. And what I mean by directly over, I mean by measuring straight up. And that's not as difficult to do as you might think. This book here, Celestial Navigation, I'm sure that most of you have seen this instrument before in movies, books, TV, magazines, something. But I was on a ship for years, so I've seen these in person. Now, when I was on a ship, we had a system of radio towers that told us what our location was, and we rarely did that. I think it was like guys that were into navigation had to do that as part of some kind of system for getting a Navy merit badge. But people did do it. And to this day, they still do it. Officers, deck officers, navigators have to qualify on a sextant just in case of an electromagnetic pulse knocking out the system that they're currently depending on. And the way that works, you've got basically a tube, like a telescope, with a piece of glass in each end of it, magnifying glass. It's like a rifle scope. It's got crosshairs in it. And you look through that until you can see the horizon. And you get those crosshairs perfectly aligned with the horizon, and then there's a mirror on there. And you have a little knob. You turn that knob until you can see the star that you're aiming at resting directly on those same crosshairs that you've got the horizon in. Once you do that, you look at the side of it, there's a number on there. You take that number and you compare it to one of these charts. So there's quite a detailed bunch of charts there. Actually tables, they call it. And once you can clearly identify 3 stars that are useful for celestial navigation, you can know exactly where you are. In the ancient past, it wasn't quite that difficult. Nowadays, you have to deal with the fact that the sun and the moon are not where they belong, the stars are not where they belong, things are moving in patterns that are not quite as predictable as they would have been in a 360-day year. But people, even today, can still navigate by the stars. So this is going to help us to be able to see the shape of our Earth from our backyard, and I'll tell you why. If you're on a planet here, and you're standing here, your horizon is going to be right about there. You know, it's like 2 millimeters on this because the Earth has shrunk down to such a small size for this whiteboard. But if you are on a tower, you can see a little further. And if you're looking at some kind of a terrestrial landmark, like a tower or a mountain range or something like that, then that's going to extend you even further. So if you're going to do what we were talking about earlier, just keep walking around the Earth until you start seeing things that you recognize, those kind of things are going to make it a lot easier for you. But it's still a pretty impossible task. But with stars, if we're standing here, we could see this star. We can actually see this star. And so remember, each of these stars is directly over a different spot on the Earth. So say this star is right over the Earth right here. Well, what have we just done? We've extended our range of what we can see, or not landmarks of the Earth, but celestial markers for the Earth. We're actually able to look into the sky and see all of the stars that are over this area. In fact, if we are on this planet, and these stars are as far away as we say they are, we can actually look way out, completely ignoring the hump of the Earth, and see stars that are way, way, way out here. Now, obviously these stars are going to be a little bit south of the equator if you're on the North Pole. If this person is on the North Pole and they're looking at all the stars that they can see, then they're actually seeing that much of the sky. You know, the sky that's over what they call the equator. That's if you're on the North Pole. And the same could be said if you're on the South Pole. If you're on the South Pole, you can see as much of the area of the Earth via the celestial landmarks, celestial markers, as this person can see on the North Pole. Now, this person on the North Pole cannot see these stars down here. There's no way to see around the Earth because those stars, even though they're way, way, way out, they're still going to be blocked by the Earth itself. But just keep that in mind, that from your position, you can see these stars. That may not seem like a big deal to you right now, but I promise if you just hang in there with me, this is all going to start making sense, and you are going to be amazed. Let's just start over. That looks kind of ragged. Too many markers and too many erasers. Now, how do you know which stars are which? Because if you look up there, it doesn't look like nothing but a bunch of dots. Well, let's look at one example. This is the North Pole, right? That's the South Pole. Right over this is a star called the North Star. And the reason we call it the North Star is because when you're standing at the North Pole looking straight up, you'll see that. But there's another reason. Since our Earth is spinning, all of the stars in the sky seem to be zooming overhead. But this one never moves, because that one's directly over the North Pole. You know, if the Earth is spinning on its axis, the axis isn't really going anywhere, you know. New Jersey, it's doing this. North Pole ain't doing nothing. It's just spinning around in position. So over the North Pole, you'll see this. And everybody on Earth in the Northern Hemisphere can see that star. Now, the way we can tell that that's the star is because of this, what's called an asterism, a group of stars that we call the Little Dipper. Everybody knows what the Little Dipper looks like. The tail of the Little Dipper ends in the North Star. Now, over the course of the night, we're going to see all the stars in the sky move except for that one. Now, down here, interestingly enough, is a southern star, but that southern star is so dim that people don't use it for celestial navigation. Celestial navigation only depends on, I don't even know how many stars, but it's probably around 100 that are really, really bright, really easy to find. So this one is not. The South Star is not. But directly after that comes a series of stars that are very bright, very easy to see, and that's called, just like the Little Dipper, what we've got down here is called the Southern Cross. Constellation Crux. It's the smallest constellation that exists. Now this is a constellation. A constellation is, you know, like Libra, Taurus, Gemini. This is an asterism because it's not actually a constellation. Constellation is a Little Bear constellation, and the Little Bear constellation has a whole bunch of other stars in it, and they kind of look like a bear. And so I guess the nose of the bear is the North Star. I think that's the way it's organized, but I'm not really sure because I'm not familiar with that. I guess I should have looked at the Big Bear so I could draw it out like I knew what I was talking about. But anyway, here, once again, this is the Little Dipper. Not to be confused with the Big Dipper, which is, I think, over here somewhere. Much bigger. That's the one that you're going to see. If you go outside and you're in the Northern Hemisphere and you look up, about 9 months of the year you can see at least part of this. And it's very obvious. I mean, if you go out there, it's like dot, 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 and it's shaped like a dipper. Now, if you're in Europe, they don't call this Big Dipper. They call it the plow. Either way, it makes no difference. It's connect the dots, make whatever you want out of it. But curiously enough, when the Europeans got here, the North Americans called that same constellation the Big Bear, just like they call it the Big Bear over in Europe, or you know, the Europeans did. So when the explorers started coming over here, the North Americans were already aware of that constellation and its name, even though if you look at it, it doesn't look like anything. So we know, right, that we can look up and spot that, not that star, but we can spot that asterism, and if we follow the asterism to its end, we can see the star. And every star out there is associated with an asterism, and just to show you how easy it is to figure this all out, I got a book here. It's called The Stars by H.A. Ray. H.A. Ray is a man that writes these. Used to. He's not around anymore. Curious George by H.A. Ray. So Curious George decided he wanted to make a book about stars so that even children could go out and identify the constellations. And here they are, basically. I mean, that's the way it works. Now, on the front of it, here's a good one, because I want to point something out. This is called Gemini. It's the twins. There's the ecliptic right there. But if you look up in the sky, honestly, you're going to see these two. You're not going to see any of this. You got to stare at these two for a while before this other stuff starts to show up. You know, adjust your eyes, remember what you're supposed to be looking for, and you'll eventually see all of the stars in constellation Gemini. And that's basically the way all of them work. Yeah, there you go. Show you that one. That's the Great Bear, Big Bear. But once you familiarize yourself with just a few of these constellations, you can start to recognize all of the stars around you. So here we are going to examine for ourselves what that means exactly. I said already, if you're on the North Pole, you can see, like all these stars, you can see stars that are over all these areas. They're known to be over those areas. You can prove this to yourself by going to those areas and looking up if you want. Which means that in reality, even though you cannot see the terrestrial landmarks here on the ground from the North Pole, you can see the stars that are directly over those points on the globe and be able to actually visualize half of the globe by using celestial landmarks. Now, this is for people in the North Pole. You know how many people live in the North Pole? I don't know, 1,000, and they're all living in, you know, in these man-made structures that are designed to withstand the forces of the North Pole. They wouldn't really live there if it wasn't for the government putting all that junk up there, because it's not really a very good place to live. So most of us don't live there. So what if we live like in the middle of America? That's America. This is the middle of America. And I think somewhere, like if you go to the middle of America, that's like, I don't know, Missouri, or St. Louis maybe. Maybe St. Paul, Minnesota. So what can you see from St. Paul, Minnesota? Well, once again, just like somebody at the North Pole can see half the Earth, if you're in St. Paul, you can see half the Earth. And that's like it's like if you were at the North Pole and you turn the Earth, that's what the North Pole would have in its, you know, visual range as far as the stars go. But let's just say that that's the middle of America. So you're able to see that right there. But remember, the Earth is spinning. So over the course of the night, you're going to see a whole lot more than that, because you're going to start by seeing what's over here, and as the night progresses, you'll see way around to the other side. In fact, over the course of a year, if you live in the center of the United States, the sky that you're going to see going to cover an area about like that. So you're actually able to see like 80% of all of the stars that exist on our star charts. Now, if you're really lucky, if you live down on the equator, over the course of a year, you'll see every star in the sky. There's a reason that's important. Here's the equator. You're on the equator. You can see constellation Little Dipper, constellation Crux, and every other constellation in the sky. Now, we're going to focus in on why these two in particular are so important. We're going to look at what we would see from on the horizon. So this is the North Star. And the Little Dipper, early in the morning, we're going to see this. Or early in the evening, rather. So when we first go out, as soon as the sun goes down, if we look towards the north, we'll see that asterism in the sky. Now if we wait a few hours and go back out, the asterism is going to be in a different position. The North Star will still be in the same place, but the asterism won't. It'll be going around. Little Dipper will be going around. Then by the time it's almost morning, be like that. So it'll go all the way from looking like that, looking like that, looking like that, kind of like a propeller. It's just going round and round and round. In fact, back in the old days when you just had them little black and white brownie cameras, a lot of people would go out and set a camera up and you could open the shutter on that. It's nighttime, right? So you're not going to get your film very exposed because it's night. But if you live somewhere where they didn't have street lights or anything, you could go open up the shutter of your camera, walk away, come back 6 hours later, and you would have a photograph that looked like that. Because you wouldn't just be taking still photos of this star, you would be taking a picture of this star as it moved across the sky. So you would eventually get a bunch of circles. Whole bunch of circles on your film. And you can go online, look, just go to Google and type in time-lapse North Star or time-lapse pole star. So if you ask a flat earther, why does it seem like everything's spinning around the North Star? They've got an answer. On a flat Earth model, North Pole is right here. The edge of the Earth is actually what they call the South Pole. So very obviously, everything's going east to west, and in a circle that means what you're actually doing is you're taking a picture like this. These stars are just going around and around because flat Earth can have a sky going around. After all, what they're telling us, and this is pretty universal, I'm not making this up, I'm not making fun of people, and obviously I'm not going to ask them to stick to their word because if they find out that they're wrong, they'll come up with a new story. But this is what flat Earth says. The Earth is firmly fixed, and somehow this sphere is spinning around with the stars stuck to it. So these stars are not millions of miles away and billions of miles away. All of the stars are stuck on this feature that they call the firmament. And there's only one reason that anybody would teach that. If you go back and watch any sustenance and covering videos, I have deeply covered the subject of the firmament before. In the book of Genesis, in the creation account, we are told that in the beginning God created heaven and earth. Immediately after that it says God created the seas. He created the seas that are beneath the expanse, and He created the seas that are above the expanse. And the word expanse, if you look it up, and you look at every occurrence of it as it appears in the Bible, it becomes very obvious very quickly that the word expanse simply means space. It just means the empty space that exists above our planet. And that could be the empty space within which birds fly, because it says that, the birds fly in the firmament. But some of the verses obviously are about the empty space between the earth and the moon, or the earth and the sun, or the empty space between the earth and this feature that is called the waters above the expanse. Now in the Bible, when the flood starts, we are told that all the floodgates of the heavens opened up, and flat earthers say that somehow that dome has got some kind of valve system or door system that can allow the seas of outer space to pour in. But in reality, you know, I think everybody needs to recognize the fact that the Bible was not originally printed in the King's English. It was printed in Hebrew, and then later Greek, parts of it in Babylonian and Persian. But what it actually says, on that day, the sky window shattered as if it was struck. That does not sound like floodgates opening. The sky window was shattered as if struck. Now, I'm trying to keep this as simple as possible, but that's not why I drew this down here as a representation of our oceans, because in the same verse it says that God created the oceans that were on the earth and the oceans that were above the expanse. He said, and He put all the oceans that were on the earth in one place. Currently, our earth does not look like this. First off, sky window is gone. It's very definitely gone. You can see that there are man-made things moving around up there beyond where that dome would be. But where is the dome? Well, the dome is here. The earth has not got one sea anymore. The earth is made up of mostly water because we're flooded. We're still flooded. After the flood was over, it did not say that the flood waters went back above the expanse. It says they receded. Receded means they went down. The waters that were covering the entire earth, eventually the pressure of that water pushed down the parts of the earth that were softer than others or easier to push down, making the mountains rise up. And you know, that's what geologists say anyway. When you see a mountain and it's got all these striations on it, the geologists say that's because of some great upheaval in the ancient past. Ice Age, I think they call it. But anyways, that's the reason that flat earthers primarily want to get you. There's a lot of reasons, because every single thing in the flat earth teaching goes against Bible teachings, and the whole point is just to get you to lose your faith in the Bible. Now, we already talked about that up there. Now we're going to talk about this down here. Because if you live in the southern hemisphere, you'll see that every night. Well, most nights. I think there may be a few nights, the dead of winter or whatever, where you don't see it because, well, I'll show you that. All constellations disappear from time to time, and that's because of this effect. You know, the stars that make up our constellations are not in our solar system. They're millions of miles past that. So our solar system is basically us and whatever other planets, the moon, and the sun. So when we look out at the constellations, we can only see them at nighttime. So this would be our summer here. See, the Earth is tilted that way. This is the axis of the Earth. Top of the Earth is facing the sun, so it's going to be much hotter for the top of the Earth than the bottom of the Earth. That's why we experience summer while the southern hemisphere is experiencing winter. But something else that happens when we're on this side of the sun is that we can't see the constellations that are over here. All of these constellations are hidden by the light of the sun. Everybody knows it's not like I'm making this up. If you go outside during the day, the stars are there. It's just that they're invisible because you can't see stars in the middle of the day. You know, the light coming from a star is very weak compared to the light coming from our sun. Not because the sun is brighter, but because the sun is so much closer. At least that's what science teaches us, and it sounds reasonable to me. So what happens in the winter? Well, in the winter, our Earth is over here. Axis is still facing at that angle. we're facing away from the sun, so we're experiencing cold. People in the southern hemisphere are experiencing heat. But we can now see all these stars out here, right? Because the sun ain't over there. But what about these stars over here? No, you can't see them. But the same is true of the southern, asterism and the northern asterism. We can always pretty much see the North Star, South Star if we're in the southern hemisphere, but we can't see the Little Dipper and constellation Crux. And that's only like for a few days, only on the days when the sun just happens to be positioned right to block it out completely throughout the day. And that's, like I said, it doesn't happen too often. But if we could, say if we could see it on the days that we can see it, let's look at our horizon again. If we're in the southern hemisphere, somewhere around here is a southern star, and like I say, it's invisible because it's not invisible. If you got some binoculars or it's a very clear day, very clear night, you look up there, you might be able to make it out. But right above that is going to be constellation Crux. So if you in the southern hemisphere, instead of seeing the Little Dipper, you're going to see that, but you're not going to see that all night. Very beginning of the night, you'll see that. A couple hours later, you'll see that. A couple hours after that, you'll see that. And once again, if you take camera, video camera, still camera, whatever, if you've got a thing for time-lapse photography or long exposures, you're going to end up seeing something looks very much like what we see when we look north. Now, the flat earther's explanation for why we see this in the northern hemisphere is because we're on a flat earth, the North Pole is in the middle of flat earth, the dome is spinning around. What is their explanation for this right here? And look, there's something else you need to know about this. Since in the northern hemisphere, the sun rises in the east and sets in the west, the moon rises in the east and sets in the west, well, the stars rise in the east and set in the west, which is this way. You can see that. Just go outside. I don't care if you live in a tar paper shack and you don't have a pair of binoculars. You can go outside every couple hours, take a look. You'll notice that that's what the stars do. But if you're in the southern hemisphere, what do you see? Well, you still see the same thing. Sun rises in the east, moon rises in the east, sets in the west, stars rise in the east, stars set in the west. But remember, if you're facing north at the equator, you're going to have to do this to face south. So now, even though stars still rise in the east and set in the west, they're going to be on the other side. Interestingly, you can see the southern star and the northern star from the equator. So if you are on the equator and you're looking at the southern star, and you turn around, you're going to be seeing the northern star. What about if you look straight overhead? You're on the equator, you look overhead, you're going to see this. Just so, in case there's people that are somehow dumber than me, if that's possible, we'll go ahead and draw it out all the way so there's no question about what I'm trying to get across to you. So you're looking, the entire sky is rotating this way. This is for us. We're looking north, the entire sky is rotating that way. Turn the other direction, the entire sky is rotating that way. Look straight up. The whole sky is passing over our head. What does that tell you? There is no explanation for the spin at the southern end of the Earth. Now, I have seen some explanations, and I swear I'm not making this stuff up, because I have spent a little bit of time on some flat Earth websites. And you ask them, well, how come the Southern Cross is spinning the other way from the Northern Cross, or the Northern Star, Little Dipper? I hope you're paying attention, because I want you to hear this answer, right? And, okay, I don't remember the answer, but I remember enough of the basics. It's like Captain Emerald Jones left, I don't know, some harbor in England in 1799, and he sailed all the way to Tahiti, and while on his trip to Tahiti, he stopped at 30 degrees latitude, and he never recorded in his log that he saw the Southern Cross. That's the answer. Never mind the 100 million sailors that have gone past there since then and made numerous records of this. One guy didn't bother putting it in his logbook, so that's proof that the Southern Cross ain't there. Now, here's the thing, just in case you're not comprehending this. All around the Southern Hemisphere, these people are very, very proud of their Southern Cross. You've got countries down here like, I don't know how these are laid out. I think this is like Australia. And over here might be New Zealand. This is Asia up here. It's kind of like that's Europe, right, and Africa. Over here is the Americas, you know, Canada, America, Central America, South America. There's a bunch of countries in here. Whole bunch of them. Whole bunch of countries in here, right? This is a country. This is a country. And it's like every one of those countries is so proud of their Southern Cross, because that's like their tourism dollars, you know. Millions of people every year will travel across the equator to go to church, outdoor mass, outdoor preaching, outdoor something, so they can be under the very special symbol of Christianity, the cross, while they're performing their rituals. And so all of those countries have flags. I think the flag of Australia is like its Southern Cross on their flag. There's New Zealand, Southern Cross on their flag. Several of these African nations included on their flag. Several of the South American nations included on their flag. They include it on their money. They put it on their postage stamps. It's like their biggest thing, because it's really bright. I mean, that Southern Cross is like equal to our Big Dipper. If you ever go out and look at the Big Dipper, the stars in the Big Dipper are very obviously much brighter than anything around. In the Southern Hemisphere, the stars of the Southern Cross are very bright. This is 50 centavos from Brazil. I hope y'all can see this, because it cost me like $3 to get this thing shipped here on eBay. Southern Cross, 50 centavos, Brazil. That's the Southern Cross. I don't know, can you see that? Maybe if I block the whole thing on my face, it'll focus right in on it. There you go. I can see it shining in the... Okay, this next one is... That's Australia. Oh, this is a cool one, because it's got like an Aboriginal guy on there. I like Aboriginal people. I just think they're so cool. He's looking off, and you can see Southern Cross behind him. That's Australia. So Brazil and Australia, right? At this point, I'm starting to run out of money for spending on coins on eBay. I was actually going to buy a sextant for this video, and I was like, no, that's like $100, you know. My subscribers wouldn't appreciate me throwing their money away like that. Okay, here you go. This is a really cool one. Okay, because Portugal was like the first modern naval fleet to go out and do any real exploring. That's how Christopher Columbus got here. And so as a commemoration of that time period, they minted a whole bunch of coins like this. That's a Southern Cross almost touching the rim of the coin. And the cool thing is that if you flip it over and upside down, that's a Little Dipper with a northern star almost touching the rim. I mean, this is not something that's been hidden. and it's not a lie. I mean, you think that people would be, like people in Australia would be spending these nickels all day and looking at that and going, I wonder why they put them stars on there. They know, everybody knows. This is like, and the cool thing is that while they're holding mass way over here under the Southern Cross, guess what they're doing here? The exact same time they're holding mass under the Southern Cross, because all the way around the world there are times when you can see the Southern Cross from every, because as the earth is going through winter and summer, the days are longer, the nights are longer. When the nights are really long, there are nights when everyone down here can see the Southern Cross at the same time. Now on a flat earth, very, very difficult to explain how that would work. Because, right, we got the Great Wall of Ice, right? You've got the North Star right there, so everybody in the Northern Hemisphere can see that at night, any night. And somehow, people in Africa can look straight down and see the Southern Cross, while people in Australia and New Zealand can look straight down and see Southern Cross, while people in South America can look straight down and see the Southern Cross. People write songs about the Southern Cross, It's Crosby, Stills, Nash, and Young, whenever you see the Southern Cross, right? For the first time. So what's really cool about this? Well, the cool thing about it is, I don't know, this book right here sold like, I don't know, gazillion copies. At least 100,000. You can get it on eBay for $4. They've always got about a dozen of them for sale at any one time. If you go to the library and you say, I want your astronomy book, they don't have an astronomy book. They've got an astronomy section. Let me show off some of this stuff that I studied in order to figure all this out. Encyclopedia of Space and Astronomy. That's like a 10-pound book I got for $4. Astronomy for Dummies. Very similar to Curious George's Astronomy. Backyard Astronomy. The Star Lore Handbook. Stars and Planets by DK Eyewitness Books. So, it's like, okay, if for a fact the Southern Cross wasn't there, if our solar system, our universe looked differently than it actually looks, at some point, somebody's going to be opening this book and looking at it and say, well, wait a second. I don't see constellation crux. Somebody's going to complain and want their money back. And these are like for me, this is a $4 eBay book. When it came out, this one was $18.95 for that when it came out. But even more important is that up until about the time of, sometime after World War II, men started putting radio towers in a grid pattern all over our planet so that U.S. naval ships could navigate the seas and know exactly where they were by bouncing signals off of those radio towers. So it was very rare. If you saw somebody using a sextant, they were just trying to get their merit badge. It's not like they had to use sextants to get around. But about the time of World War II, when they had millions of people out there traveling the oceans and tens of thousands, if not hundreds of thousands of ships, everybody was using a sextant. Now, you can go get a sextant for $100, plastic sextant, used. The one that's on the cover of this magazine, you could probably get for $1,500, $2,000. And the ones the military use are probably $1 million, kind of like them toilet seats they buy. But the thing about that is the charts. It's like these charts come out monthly, I think. I'm pretty sure that they produce them monthly. Maybe they produce them yearly. But the charts that the Navy use to do this, they ain't 18 bucks. A set of charts on a ship is probably $1,000. You know, I mean, it's ridiculous. I can tell you it's a ridiculous cost. And I've been up on the bridge when these guys are plotting their course, and they have stacks of these things. And once they plot their course, they fold them up and file them. This stuff is kept on file forever. And these charts they're a one-time use thing, and it's over with. If the Southern Cross wasn't there, if the Little Dipper wasn't there, if none of these stars were there, then somebody somewhere would have figured it out, especially if ships started sailing off and never coming back home, because remember, this is the only way these folks had of finding their way back. And the two pivotal stars of the whole system are the Northern Star and the Southern Star. Those are the ones everybody goes by when they're trying to figure out get their first idea of where they are in the middle of the ocean. There is no explanation for this. The Earth is a sphere. You can go out in your yard and see that it's a sphere. And look, I already said that if you're in St. Louis or Minneapolis, St. Paul area, I guess that's where about the center of the United States is. Probably that's the center of the population. But most of us don't live up that north. I mean, I don't. I live in South Mississippi. But if you're living in the United States, it's Florida, right? It's California over here. That's Texas. Here's Hawaii. If you live in Hawaii, which is part of the United States, you live in South Texas, which is part of the United States, you live in Miami, which is part of the United States, you know what you can see from your house? You can see the Little Dipper. And because you're so close to the equator, you can still see constellation Crux. You can see from these locations, you can see almost every single star in the sky. You can compare what you see to the charts, which are designed in the shape of a sphere, not because they're trying to trick you into thinking that the sky is shaped like a sphere, but because the Earth is a sphere, and you have to base your navigational instruments and navigational charts off of the shape that your Earth is in. Now, when you're looking at Crux, you're not going to see the Southern Star from anywhere in the United States, because the Southern Star would be hidden behind the Earth. The Crux would actually be sitting right on your horizon. In other words, if you're at the southernmost tips of America and you look out over the horizon, you're going to see this. Hello? Let me call you back in a minute. I'm making a TV show. All right, bye. Okay, where were we? Oh yeah, if you're looking out, if you're in the United States somewhere, and you look out there, you're going to see Crux come up in the evening. Like, remember, this is still east, you're just looking south, so everything's going to be backwards. Middle of the night, you'll see it here. Right before morning, you'll see it over here somewhere. And I mean, I just want you to think about that. Think about what that means. That's a really big deal. And after you've had enough time to process that in your head, take a trip via the internet to a couple of flat earth videos and try to find out what they say about this stuff. You're going to find that what I just told you is exactly what they say. You will never find somebody in flat Earth explaining why our sky looks the way it does, because it cannot, it physically cannot work on a flat Earth model. In fact, it wouldn't work on a diamond-shaped Earth or a triangle-shaped Earth or a box-shaped Earth. It can't work on any kind of model except for a spherical Earth that is spinning on its axis if the axis runs through the north and south poles. That's the only way that our solar system or our universe can look the way it does and make any kind of sense. I'll tell you what, it won't make sense on a dome. You cannot have all the stars in the sky doing this and then get to some point. There's no way in the world to make the other half of the dome go the other direction. And you certainly aren't going to be able to see Southern Crosses every couple of 100 feet all the way around the planet. Oh well. That's all I got to say, I guess. I probably had more to say before the phone rang, but that's okay. This is pretty much covers everything. And as always, if you don't want to survive, don't listen to me.